One of the more reliable types of overcurrent protective devices is the fuse. The fundamental element of a fuse consists of a fusible link or links enclosed in a tube and connected to contact terminals. The electrical resistance of the link is very low, and it acts as a conductor. When current in the circuit exceeds the fuse size, the link melts and opens the circuit to protect the conductors, other circuit components, and equipment. In this program, we'll discuss the various types of fuses in use today, explain how they work, illustrate how they're tested, look at the types of service they are used in, as well as safety precautions to follow when working with fuses. As a general rule, fuses are stable and do not require periodic maintenance or testing. Fuses have three very unique performance characteristics. First of all, they're safe. Modern fuses have extremely high interrupting ratings and can withstand very high fault currents without rupture. Secondly, when properly applied, fuses can prevent large power outages. If properly sized, only the fuse nearest a fault opens. Upstream fuses, feeder or mains, are not affected. And finally, fuses provide component protection by limiting fault currents to low values. Most low-voltage distribution fuses are rated at 250 or 600 volts. Other ratings are 125 volts and 300 volts. The voltage ratings of a fuse must be at least equal to the applied circuit voltage. The fuse rating can be higher, but it can never be lower. For example, a 600-volt fuse can safely be used in a 208-volt circuit. The voltage rating of a fuse determines the ability of the fuse to suppress the internal arcing that occurs after a fuse link melts and an arc is produced. If a fuse is used that has a voltage rating lower than the circuit voltage, arc suppression will be impaired. Under some fault current conditions, the fuse may not safely clear. All fuses have specific ampere ratings. When selecting the ampacity of a fuse, consideration must be given to the type of load it carries and to code requirements. The ampere rating of a fuse may not exceed the current carrying capacity of the circuit. If a conductor is rated to carry 20 amperes, then a 20 ampere fuse is the largest that must be used. The interrupting capacity of a protective device must be able to withstand the destructive energy of short-circuit currents. If a fault current exceeds the current interrupting capability of the protective device, the device itself may actually explode, causing damage to equipment and a hazard to personnel. This is why it's so important that only fuses or circuit breakers which can sustain the largest potential short-circuit current be used. Cartridge fuses are available in a wide range of types, sizes, and ratings. Generally, these fuses can be classified as one-time fuses, renewable fuses, dual-element fuses, current-limiting fuses, and high-interrupting capacity fuses. One-time cartridge fuses consist of a tube of vulcanized fiber, paper, or some similar material within which the fuse is mounted. The fuse terminals are connected to contact pieces at the ends of the tube. An insulating porous powder surrounds the fuse and fills the tube. When the fuse blows, the powdered material quenches the arc. One-time fuses are available in ratings from 1 ampere up to and including 600 amperes and are used on circuits with a maximum voltage of 250 or 600 volts. These fuses have very little time delay and are therefore used on circuits where faults occur infrequently. Renewable cartridge fuses are designed so that the blown fusible element can be replaced. They are available in ratings from 3 amperes up to and including 600 amperes and are used on circuits with a maximum voltage of 250 or 600 volts. Most renewable type cartridge fuses operate on a time delay system. The time delay is accomplished by a special link construction that combines parts having a heavy cross-section area and parts having a very reduced cross-sectional area. These fuses usually have heavy lag plates that are attached to the center of the link. The principal blowing parts of the fuse are near the terminal. The heavy lag plates keep the center of the link relatively cool. A reduced section in the center of the plate is designed to prevent an increase in current carrying capacity of the link. As a result, the lag plates serve only to help the terminals conduct away and temporarily store some of the heat generated in the weak spots. The additional amount of time it takes to heat the weak spots sufficiently enough to blow gives this type of fuse its time delay function. Dual-element type cartridge fuses combine a thermal element for protection against overloads of up to 800% of their rating, along with a fuse link element for protection against heavier overloads and short circuits. A dual-element fuse consists of two copper links located at both ends of the fuse container. A heavy copper center strap is held in position by a soldered connection to a spring. The soldered connection acts as a thermal element. The copper links in the end sections provide the short circuit element. Moderate overloads will not blow the short circuit fuse element, but will open the circuit by the action of the thermal element. When the center strap is heated to the melting point of the solder caused by the light overload, the spring releases the thermal cutout portion, opening the circuit. Because the heat coil and center strap are quite heavy, it takes a considerable amount of time to raise the temperature of the strap sufficiently enough to melt the solder. This feature, together with the time required to melt the solder, gives the fuse its time lag feature. On heavy overloads, however, the fuse link blows immediately, before the thermal cutout portion has time to function. Dual-element fuses provide highly effective protection for most circuits, including mains and feeders, as well as motor branch circuits and the overload protection of the motor itself. Their long time lag prevents useless shutdowns caused by ordinary fuses or breakers opening on motor starting currents or other harmless overloads. They will hold even if all motors on a circuit were to start up at one time, yet they protect against short circuits with all the speed of an ordinary fuse. Fuse enclosures should be checked periodically. Before beginning the inspection, be sure that the circuit is de-energized, locked out, tagged out, and grounded when required. Visually and mechanically inspect the fuse holder. This inspection should include an examination of the fuse terminals and fuse holder clips for discoloration, corrosion, tightness, and overall mechanical integrity. Mechanical inspections may include an insulation resistance test to check the quality of the insulation system of the fuse holder to the fuse enclosure. Another type test is a contact resistance test. This test is performed to check the electrical integrity of the fuse element as well as the contact surface area between the fuse holder and the fuse itself. Care must be taken not to exceed the current rating of the fuse. As we said at the beginning of the program, the fuse is a very reliable overcurrent protective device. When properly applied and maintained, it will provide the amount of protection necessary to protect the equipment in our plants.